Alright guys, this is video 2 for day 1 mega review. So first off, ignore kind of what I have up here. I made a mistake at the beginning, so I've started over. So we're looking at number 7. What is the empirical formula of a molecule containing 40% carbon, 6.72% hydrogen, and 53.3% oxygen? So you can see I've already started this part here. What I've gone and done is anytime we see empirical formula, what we're going to do is just change the percentages. Instead of having percent, we're just going to assume that it's grams. What this does is allow us to assume we have a nice clean 100-gram sample of whatever this empirical formula is. So the 40 grams of carbon, 6.72 grams of hydrogen, and 53.3 grams of oxygen should all equal up to 100 grams. That make it nice and easy. So now that we have these as grams, we want to make a formula that compares the amounts of these. But as we know, we can't compare stuff by using grams. So what we're going to have to do is convert all of these first to moles and then make a ratio. So beginning with carbon, we have 40 grams of carbon. And carbon has a molar mass of 12.01 grams per 1 mole. So carbon is going to come out when we calculate this 40 divided by 12.1 to about 3.33 moles of carbon. So now let's do the same thing for hydrogen here. We have 6.72 grams of hydrogen. Hydrogen weighs 1.01 grams. Again, this is just stuff you can find in the periodic table. 1 mole of hydrogen. So 6.72 divided by 1.01 gives us 6.65 moles of hydrogen. And our last step, 53.3 grams of oxygen. And we're going to divide that by its molar mass of 16. Excuse my crowdedness on here. So 53.3 divided by 16 gives us, again, 3.33 moles of oxygen. Now, we can make a ratio here by taking whatever came out the smallest, which in this case is both the carbon and the hydrogen, and we're going to divide each of these by this smallest amount. So we end up with 3.33 divided by 3.33. That's obviously going to come out to 1. 6.65 divided by 3.33 as well. That's going to come out to about 1.998 or something like that. So we're just going to round that to 2. And obviously this is going to come out to 1 as well. So there's our ratio. We have 1 to 2 to 1. So when we write that as a formula, we just make it CH2O. And that is our final empirical formula. All right, number 8. A lot of people really freaked out when they first looked at number 8 because all we did was look at this big, huge number. But really, guys, this number doesn't matter at all if you actually read the question. So number 8 says, what is the percent composition of nitrogen in a gigantic number of grams sample of aluminum nitrate? Now, guys, it doesn't matter how much our sample is. This could have been 2 grams. The answer is still going to be the same because we are looking for the percent composition. So when we're trying to find a percent, it doesn't matter how much this is. You're just going to solve this the way you would normally do any percent composition. So we're going to look at aluminum. We have 1. Nitrogen. We have, don't get tricked here because we have this subscript outside of our little basket here. So that 3 goes to the nitrogen. And then we have 3 times 3 oxygen. So oxygen, we have 9. I almost wrote a 6 there. So what we're going to do, just to be sure, we're going to look at all of our molar masses. We're going to go to ptable.com. So we have aluminum here. Aluminum is going to be multiplied by 26.98 grams. Nitrogen, we're going to multiply by 14.01. And oxygen, we're going to multiply by 16. Don't forget to multiply out before you add all those up. So this one's going to stay 26.98. 14.01 times 3 gives us 42.03. And oxygen 16 times 9 is going to give us 144. When we add those up, we come to a grand total of 213.01 grams. Now, this is the molar mass of aluminum nitrate, but what they're asking for is just the nitrogen. So we want to see what percent nitrogen plays in this. So for this, remember, we have part over whole. The part we're looking at is nitrogen, which came in at 42.03 grams, divided by the whole thing, which is 213.01 grams. So 42.03. And guys, make sure you put the numbers in the correct order here. The order matters. We come out to about 0.1973. And as we all know, to make a decimal into a percent, we're just going to move that over 2 spaces, and we end up with 19.73% nitrogen. All right, next one, number 9. We've got molecular formulas and we've got empirical formulas. So vocabulary terms, things we need to know. So for us to do this, we have to know that an empirical formula, in this case NO2, is going to be the most simplified version of a molecule. So if this is the most simplified version, the molecular formula is going to be something bigger. It's going to be some multiple of it. So if the empirical formula is NO2, the molecular is going to be some number times NO2. And this number it's going to affect the subscript. So we're going to multiply this number times N subscript, and we're going to multiply it by oxygen's subscript. So for us to figure that out, we need to know the mass of this because it is giving us the molar mass. That's basically just the mass of the molecular formula. So this has to be higher than the mass of this. So what we're going to do real quick is find out the mass of this. So nitrogen. Nitrogen is 14.01. We have 2 oxygen. Oxygen weighs 16. We're going to multiply that 16 times 2, which gives us 32. So our empirical mass is going to be 46.01. Now, what we're going to do is compare that to our molecular mass. So we want to see how many times larger this is than this. So for us to do that, all we do is divide. So 92 grams divided by 46, and I'm just going to leave off the 0.01 because it's going to come out to a nice clean 2 when we do it this way. So N is equal to 2. When we plug that in, we have 2 times NO2. That's just going to make it N2O4 when you multiply out. And that will be our molecular formula. Number 10. Which of the following contains the highest number of particles or atoms? So we want to do the individual number, not the molecules. So essentially here, guys, what we would have to do is multiply all this times 6.02 times 10 to the 23rd, and then multiply it by the number of atoms in each molecule. So since we're doing that to all of these, it really doesn't make sense to do all that. So we're going to make a shortcut here, and we're just going to multiply each of these by the number of atoms. Now, you have to remember that inside each molecule, this molecule is made up of atoms of different elements. The number of atoms is determined by the subscripts. I feel like we kind of forget that sometimes. So what this is literally saying for this methane, CH4, is we have 1 carbon and 4 hydrogens, giving us a total of 5 atoms. But we have 6 moles of it. The moles we would multiply by 6.02 times 10 to the 23rd, but like I said, we're skipping that. So we're just going to instead just multiply 6 times 5, and we're going to get 30. Again, this is a lot of assuming, but that's okay because math is always going to stay the same. So for this next one, we count how many atoms, singular atoms, are in aluminum phosphate. So we have 1 aluminum, 1 phosphorus, and 4 oxygen. That's going to give us 6 atoms. So this one will also come out to 30. Next one, we have lithium oxide. 2 lithium, 1 oxygen. We have 3 atoms. Also coming out to 30. And last, we have the ugliest molecule of all, iron 2 oxide. We have 15 moles, and this is 2 atoms. And yet again, it comes out to 30. So in the end, it's a wash. All of these are the same, and none of them actually contains the highest number of molecules. Trick question. Number 11. How many oxygen atoms are present in 0.5 moles of calcium nitrate? Now, this is where we ended up getting a lot of confusion when we were doing our different conversions. So this is going to start off like normal. So we're going to ignore the oxygen part. We're going to get this to something that we're used to handling. So calcium nitrate. First off, you got to know the formula if you're going to do anything here. Otherwise, everything is going to be messed up. So calcium nitrate. Calcium comes in at a +2 charge, and nitrate, NO3, one of our polyatomics, has a -1 charge. In this case, we do have to pop, drop, and swap, so we're going to end up with Ca NO3 2. So let's look at our mole map here. We have moles, so we're right here, and we want to get to essentially molecules, formula units. So that's going to be a one-step train track. But then we're going to add something else to it so we can figure out how many oxygen atoms there are. So start off with 0.5 moles of CaNO3 2. That's going to put moles down here. And we're going to put molecules up here. I'm going to leave it at molic. So remember, for molecules, we're always going to put 6.02 times 10 to the 23rd. Moles is going to get 1. Now, we're going to take this one step further because we're not really interested in the molecules here. We want to know how many oxygen atoms this is. So we're going to go back and make a new conversion factor. So we could see in one molecule of CaNO3 because of this subscript here and this subscript here, we have 6 atoms of oxygen. And that's our new conversion factor because that's what we want, atoms of oxygen. So 6 atoms of oxygen over 1 molecule of CaNO3. And now we're just like normal. We're going to go ahead and cancel out everything of our units that can cancel out. Now we're just typing it into the calculator. We have 0.5 times 6.02 times 10 to the 23rd times 6. And if we typed everything in right, we should come out to a total of, running out of room here, 1.806 times 10 to the 24th. Don't forget your units, atoms of oxygen. All right, finally on this page, we need to know what is the mass of 2.91 times 10 to the 25th molecules of sulfur pentafluoride. So again, the first thing you have to do here is know the formula. Now we've got sulfur and we've got fluoride. So here we have a covalent bond. So when we do that, we have prefixes to help us out. So sulfur is by itself, so we just have S, and penta means 5, so we have S, not P. We have SF5. So now we've got our mole map. We're starting off on molecules. We want to go to grams. That's 2 steps. So 2.91 molecules of SF5. We're going to go from molecules to moles. We're going to go from moles to grams. Bring down your units. Bring down your unit. Fill in your numbers as needed. So moles always gets 1. Molecules gets 6.02 times 10 to the 23rd. And grams is going to be the molar mass of this. So we need to take the molar mass of sulfur, which we're going to look is 32.06, and the mass of fluorine, we can just round that to 19. So let's go out here to the side. 32 plus 19 times 5, which gives us 95. I forgot my 0.01 here. 32.01 plus 95 gives us 127.01. That's not going to change too much, actually. So 127.01 is our final spot there. Type it in the calculator. Guys, we've got a large exponent here at the bottom. You have to make sure that you put that in parentheses. So 2.91 times 127.01 divided by 6.02 times 10 to the 23rd. And you know what? I almost made a bad mistake there. You cannot leave this as 2.01. This has to be written as the full thing. That would have been a major boo-boo. So, to reiterate, it's 2.91 times 10 to the 25th times 127.01 divided by 6.02 times 10 to the 23rd. I'm going to have to recheck this. I've got 6,139 grams of SF5. Let me retype this just in case. Yep, so that should be our good final answer. So our final answer is 6,139 grams of sulfur pentafluoride. That's going to be it for page 2.